so I'm Ethan Jackson, and I'm going to talk a little bit about Kelda, which is a project that a new startup that I started out of Berkeley. A little bit about me before I get into it. I'm a committer on the Open vSwitch project, a PhD student at UC Berkeley, and then co-founder of this startup. And I think the reason Kelda might be interesting to this audience is we're pretty heavy users of OVN. So hopefully this can be like a nice experiences talk for this community. Okay, so before I get into OVN, I'm going to motivate Kelda a little bit and talk about what it is for context. And then I'll go into how we use OVN and our experiences with it. So we've seen this rise of open source distributed systems that came along with the introduction of the cloud. So Spark for big data processing, Elasticsearch, Redis, all these things. And if you're building a sort of modern scalable application in the cloud, basically what you end up doing is choosing what off-the-shelf open source projects you want to use and then writing some code to cobble them together. And then once you have this architecture, you have to figure out how to actually get it running in the cloud. And what you really want is like a really simple, like, put this in the cloud button, right? So you call cloud.deploy and it gets up there. But in practice, that's not really how it works. To figure out how to deploy these complex distributed systems, you have to really understand them at a fairly deep level, right? So you might like read some documentation, and then read some more documentation, and then try it out. And it doesn't quite work, so you try again after checking some more blogs or tutorials. And then maybe you might get it almost exactly right, but you're having some performance issues, so you ask your friend on Slack. And finally, you kind of get it running in DigitalOcean or whatever. Finally, you get it kind of running, but you aren't totally confident that it's working. So the high-level point is running complex distributed systems in the cloud require a fairly deep amount of expertise, and acquiring expertise is hard. Okay. And we don't actually have the same problem with code, right? So if you'd like to build a database, run a database, you don't like read the latest literature on NoSQL key value stores and then write your own database, unless you've been writing OVSDB a couple of years ago. Most of us just clone some database software and then like figure out how to get it running. So acquiring code is easy, but acquiring the expertise necessary to run code in production is hard. So the key idea of Kelda is that we'd like to package the expertise necessary to run complex distributed systems in code so that it's shareable, so that people who aren't experts can run complicated systems without having to understand them. Specifically in our project, we use JavaScript. It's a super popular language. And as a result, basically, the user experience for this thing is if you're a user who wants to run Apache Spark, you use JavaScript standard package manager to pull some Spark code onto your system, and then you import Spark into your sort of broader architecture, and then it'll deploy to the cloud. And all of the details about what configuration files to set and what ports to open and how to integrate it with HDFS and all these sort of complicated things you don't have to figure out. Okay, that's kind of the high-level idea of the project. It breaks down into two broad components. First is what we call a blueprint library, which is the actual way that we envision this expertise will be encoded in JavaScript. This is the real important part of the project. But since this is the OVS conference, I'm going to mostly talk about what we call the deployment engine, which is responsible for taking this expertise written in JavaScript and actually getting the system up and running in the cloud. And that piece uses Oven. So very quickly, what the deployment engine is. Well, never mind. So the goal of the deployment engine is to make it really, really dead simple to deploy these blueprints anywhere. We want sort of single button, Cloud for Dummies deployments. We currently support Amazon, Google, and DigitalOcean, and we want to support Azure and Kubernetes and Mesos and OpenStack and basically any sort of platform that can run compute workloads. Excuse me. And a key goal of this is portability. For the expertise sharing to really work, we need an expert to be able to write a blueprint in their preferred infrastructure, and then someone else to be able to consume that blueprint and run it, say, in Google, even though the expert wrote the system in Amazon. And a lot of people have tried to build some sort of portable interface to the cloud before, and it's actually a really hard problem. And the reason it's difficult is all of the different cloud providers have like dramatically different APIs that are based on fundamentally different abstractions. They have different feature sets that they support or don't support. And then you get into the container orchestrators that are completely different. So I fundamentally believe like this problem is not solvable, building a universal cloud API. So what we do instead is we rely on the insight that while cloud providers are dramatically different, x86 isn't. So an Ubuntu VM in Amazon looks a hell of a lot like an Ubuntu VM in DigitalOcean. So the way Kelda achieves portable deployment is we rely on just Ubuntu being consistent everywhere. And then everything else we need from the infrastructure, we try and build by virtualizing on top of Linux. And that's where Oven comes in. Oven is one of the most important, or networking is one of the most important things to get right when deploying a distributed system. And by running Oven on top of Ubuntu VMs, I can write code that configures Oven and then have confidence that it will work in Amazon or in DigitalOcean or with virtual machines in my laptop. And that is awesome. Okay. So that's why we chose Oven. I'll spend a quick slide on the architecture of this, which shouldn't be too surprising. So we have, not shown here, something called the Kelda daemon, which when you deploy a blueprint, creates a bunch of virtual machines in a cloud provider, creates some masters, which run the Oven controller and our Kelda controller and a container scheduler, and then a bunch of worker VMs, which run application containers and OVS. And then in logical space, so this is the virtual network that Oven creates, it's just dead simple. A giant L2 switch. There's a load balancer, if you'd like it. Oh, are one of my containers missing? No, okay, good. And then we do microsegmentation. So every container port has extremely strict ACLs that are described in the blueprint that say exactly what other containers that container is allowed to talk to and on what ports it's allowed to talk to. And this works really well. We had to make some minor tweaks to OVS and Oven to get it to work, which I'll talk about in one slide just to be a little bit interesting, but this has worked really well for us so far. So a couple of customizations we made that might be interesting to the community. The first, Kelda is sort of a container native platform, so we're much more comfortable dealing with containers than systemd or init.d. So we actually created an OVS container that you can use on, you can find on Docker Hub. It's kelda.io/OVS. And we actually run OVS vSwitchD and Oven NorthD and an Oven controller and all these various daemon processes in Docker containers. And that works really well for making sure that running these systems is consistent wherever we're going. We had to do a bunch of work to get STT working in the cloud. For those of you who don't know, STT is a really performant tunneling protocol, sort of like VXLAN, but fast. Since Oven's booting these Ubuntu VMs, and we don't control the image of these Ubuntu VMs, getting STT working was really difficult because it requires some sort of custom kernel modules. So we actually build those kernel modules when the virtual machines boot, which was a bit of a hack, but seems to work pretty well. And then the last thing we do is, especially when we started using Oven, it did not support all of the features we needed. So we actually have our own integration bridge that sits in between the containers and the oven-controlled bridge. So when OVS receives a packet, it goes through our OpenFlow tables where we do sort of custom Kelda-specific stuff before passing it on to oven. I'm hoping we can get rid of this in the near future, but for now we're stuck with it. Okay. So that's kind of what we're doing. I'm going to spend kind of the last half of the talk giving my general impressions of Oven as a user, having used it for maybe like 2 years working on this project. So I'm going to kind of break it into like things that I think are great and things that I think could be slightly improved. So good stuff. Oven is extremely stable. I've been really, really impressed by it. In the time we've been working on Kelda, I've run into far more Linux kernel panics than Oven crashes. I don't think we've had one Oven crash, actually. I don't know how that's possible, but like, great job. It's also, not only is it very stable, it performs particularly well. This isn't an Oven-specific thing, but more of an OVS thing. So in this table, we're comparing OVS versus the standard native Docker performance versus a native virtual machine on Amazon with C4.8x large VMs, which are pretty big virtual machines. And the really important row in this table is the private IP. So that's the case where you have two containers on different hosts that are talking to each other. And OVS is quite a bit faster than native Docker. And I think that's just because it's like, well, native Docker uses IP tables and OVS is faster than it. That's why. Cool. So that's great. I don't have any slide on this, but the Oven control plane, with some caveats, has also performed pretty well for our use case. We're running at fairly small scale, like sub 200 nodes, but it's not our bottleneck, except in one important use case that I'll talk about later. And then finally, the roadmap has been really nice. When we started using Oven, it was still in beta. And I had to personally hack up a bunch of features that weren't in Oven. Almost all of those features that we need are being implemented. So that's great. I can delete a bunch of code from Kelda that's kind of ugly, and I'm excited to do that. OK. Oven's a new project, so there's always things that can be improved. So like, take these slides in the spirit of encouragement. But a couple of things that we've noticed about the project that I think could be better. So one is ACL scaling. In the days before address sets were added to Oven, ACLs were a huge, huge, huge problem for us. So if you think about a collection of containers, if you're doing microsegmentation, you have n-squared pairs of containers. So you have roughly O(n)² ACLs for each n containers that you have. And even for relatively small scale, like a 64-node Spark cluster, before address sets, Oven just couldn't boot it in a reasonable period of time because it would spend too much time dealing with ACLs. In modern Oven, because address sets were added, the control plane is actually really, really fast for this use case, and we do pretty well. The only concern I have is the data plane in the case where you have large numbers of ACLs. So on a 128-node Spark cluster, which is pretty small scale, we see 600,000 OpenFlow rules in the data plane. And I suspect that will grow exponentially as scale goes up. So that's something I'm a little concerned about. Language support for OVSDB. So I had not seen the previous talk when I wrote this slide, so it looks like DigitalOcean is doing some great work to make this better. Thank you. I will use your stuff. But anyway, at a high level, I just want to make the point that Go is becoming a really, really important language because it's become sort of the de facto standard language in the container community. So Docker's written in Go, Kubernetes is written in Go, etcd is written in Go. And anything that we can do to make OVS easier to interact with from Go will be a win from an adoption perspective. And I think a really dumb, simple thing that could be done is to migrate away from JSON RPC toward gRPC, which is, they're almost exactly the same thing, but gRPC is a little bit more modern and has the advantage that it's really easy to interact with from nearly any programming language. And then the final point that I think is actually somewhat subtle, but I think really important. So I've kind of been spending more and more time in the container community from having working on this project. And I think Oven really could position itself a lot better if it put just a little bit more effort into marketing. In the container ecosystem right now, there's this like slugfest between a huge number of networking projects. And frankly, from my highly biased position as an OVS committer, I think most of them have an inferior architecture and implementation to Oven. I think Oven is actually the best way to do networking for containers. The problem is, like, the people in the container ecosystem are mostly server people. They aren't networking people, and they just haven't heard of the project. Oven doesn't make it easy to be found. If you, like, Oven doesn't have a website. If you Google Oven, for me, the first thing I get is an SDX Central article and a man page. And some of the competing projects, I'm thinking of like Calico. If you go to their website, there's like a cute cat with like a getting started button. And it's like very friendly. You're like, ah, these people care about me. So those things are stupid. They shouldn't matter, but they do. And they don't take a lot of investment. And I'm really nervous about an inferior project ending up winning in the container ecosystem for bad reasons. So little things like getting a website together, and the only other thing I would say on this point is documentation. The documentation for Oven is fantastic for the primitives, right? Everything that's in Oven is supremely well documented. What is not as well documented is I'm someone who doesn't understand OVS. How do I take these primitives and hook them together to solve a problem I have? How do I attach a logical router to a load balancer to get a load balancer that can respond to ARP, right? So that sort of thing would be really helpful. Okay, so wrapping up, in summary, Kelda is a brand new startup that's trying to encode operational expertise in JavaScript to make it really, really stupid, easy to deploy things to the cloud. We make heavy use of Oven because it provides portability for us. Check it out at kelda.io. Particularly for this community, I'd highly recommend you check it out because we're probably the single easiest way to get an Oven deployment up and running that you can sort of SSH into and poke around and look at what's going on. And with that, I think we'll take questions. Thanks.
Ethan, you've moved way up the stack from C to
I
JavaScript.
Have. Garbage collectors are awesome.
Yeah. All right. Go ahead, please.
Thank you. I'm going to leave for a plane after this, but so this is. Can you put sort of arbitrary deployment payloads on this, or is it for just specific things like Spark and Hadoop, or?
I got the second half of your question, but not the first. Can I put?
He's asking, can you put arbitrary things on it, or just specific things like Spark and Hadoop?
So the JavaScript API is fully general, and you can encode anything you want in there. We're a tiny little startup, so we personally have written Spark backend because we understand Spark really well. But the goal is that if I build a new distributed system, I will write the expertise for how to run it and put it in my sort of upstream repo, and then other people can use it. That's the long-term goal.
Cool, thanks.
Yeah.
It's kind of shocking that Berkeley grad students would know Spark well.
Oh yeah, yeah.
Hi, Ethan. This is great talk, and I should play with it because you support DigitalOcean and
great.
I'm working for DigitalOcean.
Yeah.
But anyway, my question is, you mentioned about a Kubernetes, and one of the design diagram of Kelda is kind of similar, and you also mentioned about the Kubernetes support.
Yep.
Can you give me the relationship and what is different and what kind of abstraction you
Yeah,
can
yeah, yeah.
provide?
Okay, so as the leader of Kelda, the thing I actually care about is the JavaScript API. That's the important part of the project. We have our own deployment engine, which is fairly similar to Kubernetes plus like Terraform, which is really just an easy way for people to get started with Kelda. In the future, I expect that will continue for the like beginner non-experts, and then we'll also do a Kubernetes backend, so you can take these blueprints and deploy it to Kubernetes for people who want to use that. And in that case, a lot of this deployment engine stuff would be replaced by whatever that particular Kubernetes operator is using. But we aren't going to help you figure out which networking provider to use for your Kubernetes stuff. It'll be a little bit more work for you. Yep.
Great, thank you.
Yep.
Hey, so this looks great. Looking forward to checking it out for sure. And also, thanks for the support of DO. We appreciate it. And yeah, we'd love to collaborate on like OVSDB or whatever because we're in the same boat. So my question is, non-technical, but is Kelda based on the We Free Men like name, or where did the name come from?
The name?
Yeah.
There's some story for the name.
Okay.
It sounds good. It's happy sounding.
Cool. Thank you.
The trademark was available.
Until recently, it was called Quill, right?
It was called Quilt, yeah, which is that's a long story. That's like crap you have to deal with when you start a company. So. Yeah.
Hello. One more question. So you mentioned about STT. But since this deployment is in the cloud, so it's running a VM. So I wonder how STT would help, since STT is, the benefit seems to be like the TCP offloading.
Mm-hmm. So, okay, so we're getting into like Linux kernel territory that I don't understand as well. But my understanding is that, and if I'm wrong, please correct me, virtual NICs, VM's virtual NICs support TCP offload, which basically means the virtual NIC won't segment the packet until it gets to the hypervisor. So we're still sort of taking advantage of the hypervisor's TCP segmentation offload. Frankly, I don't know. It's faster. So it seems to improve
It's based
things.
on the testing result.
I missed that, but we did test it, and it is faster, if that's what you're
Okay,
asking. Yeah.
thank you.
Let's thank our speaker again. Thanks,
Cool.
Ethan.
Thank you.